In example 2 of 3.5, we are now going to look at intervals on which the derivative is negative. So same type of question, just instead of positive, we're looking at negative. But the equation's a little bit different here. We still have a product rule, and inside that product rule, we have some chain rule happening. But I want to talk about the difference of this equation here. The first example, we had polynomials. This is not a polynomial because you have that square root function. So I first want to talk about the domain of this function before we approach this problem. So anytime you're asked to find when a derivative is negative or something like that, or doing some type of analysis, it's important to understand what your domain of your function is. So what's underneath this square root when you're talking about the domain has to be positive, right? So our domain would be when 4 minus x squared is greater than or equal to 0. And hopefully you understand, I mean, I'll work it all out. So I'll just go ahead and say that's going to be the factored into 2 minus x times 2 plus x has to be greater than or equal to 0. And therefore, you have factors of 2 and negative 2. Remember, whenever you solve an inequality, you always want to do a number line analysis if it's quadratic or something like that. All right, so if you plug in 0, you would get a positive, and then outside of that would be negative. All right, so if I'm looking for the domain of this function, it's when the argument, what's inside, is always positive, so that would be values between negative 2 and 2. All right, so the domain of this function is only values between negative 2 and 2. So when I evaluate my number line analysis, you're only looking within that range. You're not looking outside of negative 2 and 2 because the function doesn't exist outside of negative 2 and 2. Okay, so now let's actually attack the derivative. So we're going to approach this in the same exact way that we solved the two examples in number 1. So this is overall a product rule. So the derivative of the first is 2x times, we're going to keep the second function exactly the same, plus the derivative of keep the first function the same, x squared, times the derivative of the second function. Now, the derivative of the second function is a power rule because that's raised to the 1/2 power. So we would bring the 1/2 down, times 4 minus x squared to the negative 1/2 power. Now, don't forget that the derivative of this second function involves the chain rule. So now we have to multiply that by the derivative of the inside function, which would be negative 2x. All right. Now, I'm going to kind of simplify this a little bit. So again, if I was just asking for derivative, we'd be fine, but we have to find when this is negative. And so we're going to have to do some algebra before we move on. All right, so I'm going to simplify that second term. So hopefully you see that these 2's are going to cancel. We have this negative, so that's going to change our addition to subtraction. And then we see you have the x squared times the x, giving us x cubed. And then that negative 1/2 power is going to throw that square root of 4 minus x squared in our denominator. So now we have this expression, and we want to see when this is less than 0. So I'm going to actually do one more step in order to get this into a format that's going to be easily to manipulate that. And that is, I'm going to combine these two fractions into one by finding a common denominator. So to get a common denominator, we're going to multiply that first expression by the square root of 4 minus x squared. So notice when I do that, so if I multiply by the square root of 4 minus x squared over the square root of 4 minus x squared on that first term, what's going to happen is you're going to get 2x, and then that square root times the square root is just going to eliminate that square root and give you a factor of 4 minus x squared. The other expression doesn't need, you already have the common denominator, so you're going to just subtract x cubed. And then our denominator would be the square root of 4 minus x squared. Now I'm going to clean up that numerator a little bit. So I'm going to distribute and also subtract that x cubed. So when I distribute, you get 2x times 4, which is 8x. 2x times negative x squared is negative 2x cubed. And then that negative 2x cubed is going to combine with the negative 1x cubed to give us negative 3x cubed over the square root of 4 minus x squared. And then our final step, I'm just going to go ahead and factor out our numerator in x. So we get 8 minus 3x squared. All right, so now we have completely simplified this as much as we possibly can. And so now we're finally ready to answer the question. So notice the calculus isn't too bad. It's doing all the algebra. That's a lot of work. So we want to answer when the derivative is negative. So in order to answer that, again, we want to simplify our derivative down as much as we possibly can. And then we're going to ask ourselves, when is this expression less than 0. Now, we already considered our domain. Remember, our domain of our original function is only looking at values between -2 and 2. And this would hold true for our derivative as well, because notice only values between -2 and 2 are going to be valid, because our denominator also has that square root. Notice that the domain for our derivative, though, would not include -2 and 2, because that would cause the denominator to equal 0 and therefore be undefined. All right, so all we're looking for is the factors in the numerator. So the factors in the numerator, we're going to get 0 here from this x. So when we do our number line analysis, what I'm going to go ahead and do is I'm going to go ahead and really restrict us between -2 and 2. So we have 0 is one of our values that we're going to look at as 0. And then when we have 8 minus 3x squared, think about that. If you were to solve for x, you would subtract 8, divide by -3. So let's do that. So x squared would equal, if we're setting this equal to 0, would be subtract 8 divided by -3 would be 8/3. And then we would take the square root of that. So x would equal the plus and minus square root of 8/3. Now 8/3 is smaller than 2, so that's within our interval that we're looking at. So we're just going to put that value in there as well. So I'm just going to keep it as square root of 8/3 and the negative square root of 8/3. Okay, so when I do the number line analysis, I would start off by doing testing a value of 1, since 0 is already on our number line. 1 is smaller than the square root of 8/3. So if you think 1 is going to be between here, if we evaluate our derivative at a value of 1, notice the denominator is always going to be positive. So if you evaluate at 1 in the numerator, you'll see that you end up getting a positive. After that, I would use your multiplicity. So each of the factors, positive and negative, square root of 8/3, and 0, all have a factor, only happen once. So you're going to change sign everywhere you have a value on your number line. All right, so when you're looking at when the derivative is less than 0, again, -2 and 2 are out, because that would cause the denominator to equal to 0, and then each of these other values would be equaling 0. So if I'm less than 0, that would be between this negative square root of 8/3 and 0, and also between positive square root of 8/3 and 2. So how we would write our answer, our final answer, would look like this. All right. Okay, so again, the algebra is really not friendly here. So it's good to revisit these, because again, the calculus was fairly easy at the beginning. It's the algebra that makes these pretty nasty. All right, so let's try another example here with number 3. Slightly different question, and also we have a quotient here instead of a product. All right, so it says write the equations of each vertical and horizontal tangent to this graph. We've seen an example before with vertical and horizontal tangents. So what we're going to do is we're going to find the derivative first, and then a horizontal tangent, remember, is when the derivative is equal to 0, or the numerator is equal to 0. And the vertical tangent is when the derivative is undefined, or when the denominator is equal to 0. So I'm going to let you try this derivative by yourself. So again, it's going to be quotient rule. Inside that quotient rule, you are going to have a chain rule. So try this one on your own. Just do the first line by yourself, and then we'll do the algebra together. Okay, so here's just the first line that I asked you to do. So I did quotient rule, which was low d high minus high d low all over low low. So our low function is the square root function times the derivative of the high, which is just 1. So that's why you don't see anything written there. Minus high, the x plus 1, d low. Now, when you take the derivative of the low function, which is here, you're going to do the power rule and the chain rule. So you have the 1/2 from the square root, keep the inside the same, to the negative 1/2 times the derivative of the inside. And then the denominator is low low, or the denominator squared. And since the denominator is a square root function, squaring it just eliminates the square root. Okay, so now we're going to clean this up, because we want to use this to find when the tangent is, or the derivative is 0 or undefined. So we want to get this as completely simplified as possible. All right, so the first thing I'm going to do is kind of clean this up a little bit. So that first step is, our first expression is already good. The second expression, though, needs a lot of help. So first off, see the 2 and the 1/2 are going to cancel. And then you have that negative 1/2, which means you're going to have a fraction with that square root of x squared plus 1 in the denominator. And what's left that's going to multiply together is that x and that x plus 1. So I'm going to go ahead and write that as x squared plus x. All right. And then again, all of that's over x squared plus 2. Okay, so what we have here is a complex fraction. So when you have a complex fraction, you want to multiply by your LCD of your small fractions. The only thing going on here is that square root of x squared plus 2. So I'm going to multiply by an entire numerator by the square root of x squared plus 2, and my entire denominator by the square root of x squared plus 2. Okay, so this is just our skills from algebra in dealing with the complex fraction. So when I distribute that square root times the square root, that square root's going to fall away, giving us just x squared plus 2, minus, when I distribute here, that's going to cancel out with the denominator. So we're just going to subtract the numerator. Now watch out, because that subtraction is going to have to distribute to both terms. So I'm going to write it like that for now. All divided by those two factors, x squared plus 2 times the square root of x squared plus 2. And there's really not much you can do there. Well, there's one thing, we'll talk about that. All right, so now let's simplify the numerator. Notice the x squareds cancel, and then you would be left with 2 minus x in the numerator. Now, in the denominator, I want you to notice that you could do something here, and it's going to be helpful. I want you to consider the powers here. It's the same expression, right? X squared plus 2. Let's rewrite this. So I had x squared plus 2 really to the first power times x squared plus 2 to the 1/2 power. Since these have the same bases, remember from algebra, if you have the same bases, to two different powers, you just add the powers together. So this denominator would be x squared plus 2, and then 1 plus 1/2 gives you a power of 3/2. So you could probably simplify it like that. All right, now we are not in this one finding when the derivative is positive or negative. We are finding horizontal and vertical tangents. So you're going to have a horizontal tangent, so a horizontal tangent when the numerator is equal to 0, or in other words, when x equals 2. And then you're going to have a vertical tangent when the denominator is 0. Now, if you think about this denominator, you would have x squared plus 2 as your factor, and you're trying to find when that equals 0. Well, that's never going to be true, because x squared plus 2, right, a squared plus a number, that'll never equal 0. In fact, it'll never be negative. So what this means is there are going to be no vertical tangents, because that denominator of the derivative will never equal 0. So that's the answer for the vertical side. Now let's go back to the horizontal tangent. We said there was a horizontal tangent when x equals 2, but the question asks for the equations of the horizontal tangent. Remember, a horizontal line is y equals a number. So what you have to do is now plug this into the original function to find the y value when x is 2. So that original function was all the way up here, and what I'm going to do is plug in 2 into that original function. So we would get a y value of 2 plus 1 over the square root of 2 squared is 4 plus 2, giving us a value of 3 over the square root of 6. So our answer is just y equals 3 over the square root of 6, because you have a slope of 0, so you just have y equals that number. All right, so that is our last example where we're really combining the product rule with or the quotient rule with the chain rule and all the nasty algebra that comes with that.